is we're going to look at x cubed minus 3x plus 1 equals 0. We're going to show that it has a root between 0 and 1. We're then going to derive the iterative formula. Now, they won't ask you at GCSE to just come up with an iterative formula. They'll give you it, and they'll ask you to show how it could be derived. So it's all about your method of doing it, showing you all you're working out. And then we're going to generate an approximate solution to the equation after 5 iterations, assuming that x0 equals 1. So the first thing we're going to do is we're going to show that this has a solution between 0 and 1. And the way we're going to do that is just by taking y equals x cubed minus 3x plus 1. And we're going to plug the two values that we're given for x in, 0 and 1. And we're going to substitute those in. So if we substitute in x equals 0, we find that y actually equals 1. And if we substitute x equals 1 into this, we find that y equals 1 cubed minus 3 times 1 plus 1, which is minus 1. Now, these correspond to 2 points on the graph, so it's worth going back and looking at this. When x was 0, we could see that y would have been 1. And when x was 1, we could see that y was minus 1. And therefore, to get from this point down to this one, I had to cross the x-axis, and that means there had to be a root between those two values. So if I look at this without the graph, I can see that here I was, when x was 0, I had a positive value, and when x was 1, I had a negative value, and it's this change of sign. And it can be positive to negative or negative to positive, doesn't matter which, but it will tell you that if it changes sign, it must have crossed the x-axis in between. And then I give a little explanation of this. Hence, as the line crosses the x-axis between 0 and 1, there must be a solution in this range. So I can see that there is a solution between x equals 0 and x equals 1 without actually drawing the graph. Part B of the question says, show the following iterative formula can be derived from x cubed minus 3x plus 1 equals 0. So what I'm doing here is I'm again, as I did in the previous exercise, just trying to get x equals. And I can see quite easily from the final form that I'm going to end up with down here that I need to have, I need to be dividing by 3 at some point. So if I'm going to be dividing by 3, I'll make it 3x equals. So I add 3x to both sides in this case to get a 3x here. Obviously the 3x just disappears out of here, these two cancelling out. I'm then just going to divide by 3 so that I'm dividing this 3x by 3 to get x. And this gives me 1 plus x cubed over 3 equals x. So to turn that into an iterative formula, you'll notice here I've just reversed this. I've put left to right and right to left. However, my xn becomes the thing which is kind of part of the formula, and the xn plus 1 becomes the subject of the formula. So, and that's the same every time you do this. So I've now got my iterative formula. I've now got to go and show that I can get a solution to my iterative formula. So I know that x0 is supposed to be 1. Here's my formula. I plug 1 into my original formula, 1 plus 1 cubed over 3. And remember, it's just this 1 that's cubed. It's not 1 plus 1 all cubed. It's just this 1 that's cubed. So 1 plus 1 cubed gives me 2. 2 divided by 3 is 0.6 recurring. I then take the 0.6 recurring and I substitute that into the formula. So this was my first iteration. This is my second iteration. So 1 plus 0.6 recurring cubed over 3. This gives me 0.4320. That gets substituted in to give me my third iteration. So 1 plus 0.4320 cubed divided by 3. That spits out my next iteration, and so on. And after 5 iterations, I find I've got 0.3474. Now, we're not going to comment at the moment on how good a estimate to the solution of this equation this is. We're not actually going to check it. However, what we can see if we go back to the graph earlier on is that somewhere between 0 and 0.5, there is a solution. And if I look at that, it's certainly between 0.3 and 0.4. So this looks like a fairly decent approximation of the solution.
Very typical problems. I'm going to look through these very quickly. First one we're going to look at is to prove that x cubed minus x minus 70 has a solution between 4 and 5. We're going to derive the iterative formula to solve it, and then we're going to solve it to 4 decimal places. So if you've already watched the first iteration video 1, then we've covered about how to do this. We pick the two x values, x equals 4 and x equals 5. So we say x equals 4, and then we would then pick the y value for that, using this and turning this into x cubed minus x minus 70. So substituting 4 in here, we end up with 4 cubed minus 4 minus 70. 4 cubed being 64, take off 4 is 60, 60 minus 70 is minus 10. We then do the same for x equals 5. So y would be equal to, once again, x cubed minus x minus 70, which would be 5 cubed, which is 125, minus 5 minus 70. So 125, take off 5 is 120, take off 70 is 50. And there's a sign change here from negative to positive. So I can say, therefore, there is a sign change. And I need a little sentence that says something along these lines, between x equals 4 and x equals 5. Therefore, the graph crosses the axes, crosses the x-axis to be precise, crosses the x-axis, therefore there is a route between 4 and 5. And you do need a little explanation that kind of says something along those sorts of lines. Then we're going to derive the iterative formula. Well, we start from x cubed minus x minus 70. So we always start from the same place, x cubed minus x minus 70 equals 0. We can see the last thing, everything's cube rooted. So it's pretty fair to assume at this point that they want us to cube root last. So we do everything else first. So we can say plus x plus 70 plus x plus 70 onto both sides. This is going to give us x cubed equals x plus 70. I'm now just going to cube root. So I'll just write what I'm doing. I always assume that it's best to assume that examiners are actually looking for absolutely everything possible, and all possible pieces of working out. If you leave something out, all you do is risk losing marks. This, of course, is not an iterative formula, not until I've introduced the xn and xn plus 1. I can say, therefore, xn plus 1 must be equal to the cube root of xn plus 70. And that's my complete derivation of that. You'll always be told this at GCSE. You won't have to derive them from first principles, so that's going to be absolutely fine. And then finally, solve this to 4 decimal places. Well, I'm now going to just use my iterative formula. It doesn't give me an x0 value, so I haven't decided on one of those. So let's decide that x0 equals 4, and we'll go from there. So this is the bit that people get confused with. I now know that x1 must be equal to, and using the iterative formula I've been given, must be equal to the cube root of, well, it must be equal to the cube root of x0 plus 70. Now I know what x0 is. It turns out it's 4. I'm going to show all the working out at least for the first one. So I've now got the cube root of 4 plus 70. So I'm looking for the cube root of 74. And that will give me my second value. So let's find out what that is. Now, what I don't want to be doing is typing all of this into a calculator. So I need a way of doing this reasonably easily. So what I do is I put my my x0 value into the calculator, and the way I do that is by putting 4 equals. That is now effectively the answer that I've got. So this is the ANS button on my calculator. So I can now say that I can now kind of type this formula in and say that this is the cube root of the ANS button, that, plus 70. And if I push equals, that will then give me x1, which is 4.19833. Now I want this to 4 decimal places, so I'm going to work to 5. I'm now going to say, okay, so what's x2? Well, x2 I know is the cube root of 4.19833 plus 70. So that will give me x2. Now, because I've got this already programmed in that it's taking the answer I've got, as you can, I hope you can see on the screen there, you've got the answer I've got and adding 70 on and then cube rooting the whole thing. I've already got this in my calculator because that answer is going to take that value. So when I push this again, it will give me my next value, which is 4.20208. So 4.20208. And these have obviously got more digits after them. So I can now continue with this and say, well, x3 must be, and we can continue to write this out. What you can see is this gets quite laborious quite quickly, and you're under exam pressure. So 20208 dot dot dot, I should have some dots there, plus 70. You're under exam pressure, and clearly this isn't going to go away. So I can push equals again, it will give me the next value, and that's 4.20215 dot 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 dot. I'm working to 4 decimal places, and I can see that this is really coming down very quickly. So what I'm going to do from now on, I think I've shown enough working out to be able to pick the marks up. So at this point, I'm going to stop using the working out, and I'm going to start just going to the answer. So x4 will be, just push the button again, 4.20215. And what I can notice here is that this was 4.20215. This is 4.20215. So the 4th decimal place is the same, but the 5th decimal place is also the same. And that means the 4th decimal place can never change again. And I'll show you this in a second. But this means that I can now say, therefore, that x equals 4.202, and you've got to bear in mind this is always going to be a 5. So this is going to be 4.2022 to 4 decimal places. I'm going to round that up because that 5 is going to round that up. And that's going to be my final answer. Now, if I continue and I go with x5, I can see that I get 4.2021. It's still a 5. The next one, which would be x6, that 5th digit is still a 5. x7 is still a 5, and so on. It will always be a 5 from now on. It will never change. So there's my solution.